This is PreAP, PreCalculus, Notes 4.4. And when I say notes, it's kind of a misnomer here. This is more of a review of what we've done so far in this chapter. It's putting everything together. It's the climax. It is very little new and a lot of how does this stuff all fit together. The graph of a cubic function is pictured. Use the graph to answer these questions. So we don't know what any of the coefficients are. We don't know what the constant is. Based upon the graph, what can you conclude about the values of A and D? Give a reason for your answer. Now, big picture wise, let me go through this and then I'll show you what I wrote formally. D, that's usually pretty easy. That's the constant. That's where this graph crosses the y-axis. So since this graph crosses the y-axis at 1, then D is going to be 1. That's pretty simple. I think I can write my answer better than what I have written down here. And then what conclusion can you draw about A? Well, I don't know what A is numerically, but I do know that A has to be negative. This is obviously a function of odd degree because the end behaviors are opposite. As it goes left, it goes up, and as it goes right, it goes down. And that is the end behavior that a graph has as odd degree with the leading coefficient that's negative. So let's look at what I wrote for the answer here, and then let's clean it up if it needs cleaned up. A is negative because the function rises to the left and falls to the right. All you have to say for that. D equals 1 because y is the same as the constant, which is 1. All right, good enough. That's what I wanted to say. It's perfect. B, based on the graph, what can you conclude about the roots of g of x? Well, let's check this out. This root right here is the only real root that this has. So that is a positive real root. Its multiplicity is 1 because it crosses the x-axis and it does not appear to be changing concavity. So if there's supposed to be 3 in total, and it has to be 3 because of the fundamental theorem of algebra, it means we're missing 2 and those have to be imaginary. Here's what I wrote down formally. By the fundamental theorem of algebra, g of x has 3 roots because it's cubic. So we want to know that it has 3. Let's identify the one that we know. G of x has 1 real root. It's positive with odd multiplicity. Now it doesn't say, well, it does say explain your reasoning. We might want to also say there that g of x crosses the x-axis without changing concavity. Oh, then I said it, because g of x crosses the x-axis, and I wrote it may or may not change concavity, depending on your perspective. Now, if you think that right here that it changes concavity, then we would say that it's multiplicity of 3. If you're saying it doesn't change concavity here, then we would say that it's multiplicity 1. So I think that what I would conclude from this is maybe we're not 100% sure where exactly it's changing concavity. So that's why I wrote that it may or may not change concavity, because I wasn't 100% certain. When I wrote my answer for this originally, I went a different route, but then I think a student brought to my attention, well, how do you know for sure? Because I really am not 100% positive where this is changing concavity. So my original thought was this is odd multiplicity of 1, so there's 2 additional imaginary roots, but on further inspection, maybe I'm not sure if it changes concavity there or not. Based on the graph, what's the maximum number of sign changes that the equation could have? Well, g of x has only one real zero, and it's positive. So that means that since we've already established that the multiplicity of that is 1 or 3, that means there could be 1 or 3 sign changes. G of x only has one real zero, and it's positive, so P of x must have 1 or 3 sign changes, depending on the multiplicity. D, if the coefficients of the linear term in the equation is -3, so first of all, what's a linear term? This is a cubic term, a quadratic term, linear term. The linear term is the one that makes a line, which is x to the first. So if that is a -3 and g of -1 is 8, find an equation for x. So the first thing I would do for this is, now it doesn't mention anything here about d, but we already figured out earlier that d is 1. So I go ahead and I replaced in this original function, I'm just going to bring this down just so we can see where we started from. Started from this equation here. We found out in question A that d was 1, so we put that in. We're told here that the linear term has a coefficient of -3, so we put that in. We don't know what A or B are. However, we are told that there's an ordered pair that this goes through. So we could replace, let me write that down. This is the ordered pair that it goes through. So we could replace in this equation y with 8, and each of these x's we could replace with -1. If we do that, put y in here, put 8 in for y and put -1 in for x's, and we simplify this, a -1 cubed is -1, -1 squared is +1, and a -3 times -1 is +3. 3 and 1 is 4. If I subtract 4 from both sides, then I get that 4 is equal to -a plus b. Now that presents a problem, because we want to know what a and b are, but there are two variables in this equation, so we can't solve for it. So we need to figure out a way to find another ordered pair. We are told this one. We've already used this one because we know that we have 1 is the constant. I would say that it's pretty reasonable to assume that this point right here, 1, -2, is an ordered pair on this graph. So I could say from the graph, I know that g of 1 is 2. G of 1 is -2. So I go through this process again, replacing y with -2 and replacing x with 1, simplify the equation, and I end up with 0 equals a plus b. Still not solved. Don't know what x or y are, or a or b are, I should say. But now we have two equations and two variables. That's a system of equations. So I can put those together as a system of equations. And if I stack them the way that I did, so that my a's line up, my b's line up, I can add these together through solving by elimination. And 4 plus 0 is 4. -a plus a is 0. B plus b is 2b. And then if I subtract, or if I divide both sides by 2, I get b is 2. Once I know b is 2, then I can take either this, I can take either this equation or this equation, whichever one's easier, and replace the b in it with the 2. I'm going to choose this one. If I put 2 in for b, it's going to give me that a is -2. So now I know what a, b, c, and d are. The directions were to write an equation. So my equation is g of x is -2x cubed plus 2x squared minus 3x plus 1. That is a heavy process. I don't remember for sure, but I'm pretty certain there's going to be a question like this that's a free response question on a quiz or a test to finish out this chapter. I am very confident. Consider the quartic function to answer the following questions. A. Use Descartes' rule of signs to create a chart of the possible combinations of the types of roots that f of x will have. Well, there is 1, 2 sign changes. So there are 2 or 0 positive real roots. I'm just going to write that above here. 2 or 0. And then if we put a negative x into this, for every term that has an even exponent, it stays the same. Every term that has an odd exponent, you change the sign. So we end up with a negative x to the fourth plus 3x squared. Those haven't changed because their exponents are even. Plus 2x, that sign changed from the original, minus 2. There is 2 sign changes, so that means that we either have 2 or 0 negative real roots. How many of these roots are 0? Well, there are none, because if you look here, this ends with a constant, and therefore there could not be any zeros that are 0. As far as imaginary goes, I mean, at most there could be 4. There could also be 2, or there could be 0, because there's no guarantee that there is any positive or negative real zeros. So as far as combinations go, we could go 2, 2, 0, 0. We could go 2, 0, 0, 2. We could go 0, 2, 0, 2. We could go 0, 0, 0, 4. Sketch a graph of f of x on the axis pictured, then determine which combination of type of roots from your answer and part A is correct. You have a reason for your answer. Well, this graph, I just graphed in my calculator and copied it here. Yours does not have to be as precise to scale, but do the best you can. We'll come back to later what A, B, and C are. So based upon this graph, it looks like that we have 2 negatives, and which means that we're going to have 2 imaginary. It's like we're in this because there's no positive ones. Writing this down formally, f of x is quartic, so it has 4 zeros. We are painstakingly writing down every detail. Since the graph crosses the negative x-axis twice without changing concavity, each negative root has a multiplicity of 1. You have to mention the multiplicity. So the 2 remaining roots have to be imaginary. Part C, using your graphing calculator, determine the coordinates of the relative maximums and minimums of f of x and state the intervals to which f of x is increasing or decreasing. While I used my calculator, I did second calculate maximum, second calculate maximum, second calculate minimum, rounded to 3 decimal places where I could, and I got maximum here and here and a minimum here at B. Now I labeled those with points, and you'll see why in a bit. So then, when does this graph, hold on a second. So I'm going to state these relative mins and maxes, ordered pairs. State the interval for which it's increasing or decreasing. This graph is increasing to the left of A, so that's negative infinity to negative 1.366. And then it's increasing from B to C, which is from, I think I have that written down wrong. No, I don't. It's increasing from 0.366 until it gets to 1. We're looking at x values here. When is it decreasing? Well, it's decreasing from negative 1.366 down to 0.366. And it's decreasing again right after 1 down to infinity. Increasing and decreasing intervals, never use the end values. Find the coordinates of the points of inflection for the graph of f of x. If you recall, points of inflection are approximately halfway between the x values of the 2 consecutive relative mins or maxes. So for example, I have a max at A and a min at B. So approximately halfway between A and B, there's going to be a point of inflection. It asks for the coordinates of that. So I think in the past we just found the x value, which is probably what we want, but let's just do this anyhow. So we want to find the midpoint of AB, sum of the x's divided by 2 plus sum of the y's divided by 2. So those are x values and our y values. Simplified, we end up with negative 1/2, negative 1/4, positive 1/4. That is an approximation. There's also a point of inflection between B and C. So we want to find the midpoint between B and C. And we find that to be approximately 0.683, negative 2.174. Then state the interval where the graph is concave up or concave down. It is concave down till we get to this inflection point here. So that would be from negative infinity to negative 1/2. And then it's concave down again in here, which is from 0.683 to infinity. Where is it concave up? It's only concave up in here between the two inflection points. So that's between negative 1/2 and 0.683, non-inclusive. It would help you answer these questions if there was space on your graph to actually write down the coordinates, and I'm going to do that. This was negative 1/2, 1/4, and this little fellow here was 0.683, negative 2.174. All right, similar question. Equation of a cubic polynomial is given. And by the way, f of 2 is 0. Determine the left and right behavior of the graph of f of x and justify your answer. Well, f of x is odd degree with a negative lead coefficient. That tells us that the graph looks like this. And I would draw that just to give yourself an idea of what that looks like so you don't make a mistake on this. As x goes to negative infinity, f of x is going to infinity. And I tell you what, we have written this better than this. Let me write this down the way we've been writing it. The limit of f of x as x approaches negative infinity, that is positive infinity. As it goes left, it goes up. The limit of f of x as x approaches positive infinity is negative infinity. As it goes right, it goes down. B, if f of x is divided by the factor x minus 2, what will the remainder be? Justify your answer. If f of x is divided by x minus 2, the remainder will be 0 because f of 2 is 0. This is the factor theorem. If a function is divided with a remainder of 0, then the divisor is a factor. Therefore, x minus 2 is a factor of f of x. Let's see, did I put too much information? If f of x is divided by x minus 2, what will the remainder be? So we said it was 0. Said justify your answer. I don't think that we actually need all this. I'm going to take that back. Hope we didn't write that down yet. And I think that we can just say this, and then we can say by the factor theorem. The reader is supposed to know the factor theorem. I don't think we need any of that. If I change my mind, I will let you know. All right, part C. Find the value of k in the equation f of x. Show your work. Well, to find the value of k, I'm going to take this function and divide it by 2 synthetically so I get a remainder of 0. So negative 2 plus 0 is negative 2. Negative 2 times negative 2 is negative 4. Add these, I get negative 2. Multiply, I get negative 4. Add k and negative 4, I get k minus 4. If I multiply 2 times that, I'm doubling each of those. And then if I add these together, I get negative 2. I get positive 2k minus 4. This remainder, 2k minus 4, is supposed to be 0. So if I simply set that equal to 0 and solve it, I'm going to get k equals 2. Determine all the roots of f of x. Show your work. Now, when I do this, I definitely want to include, probably want to write this down, and I don't want to write k anymore. I want to write that this is a 2 because that's what it is. So to determine all the roots, we know that one of the roots is 2. So if we divide this by 2 synthetically, and instead of having a k in here, we now have a 2, we're going to find that it goes evenly, which it should. If we then take our depressed polynomial and we write it as a trinomial, so we have a factor of x minus 2, because 2 is a root, and then we have this depressed polynomial, which is now a trinomial. We could factor a negative 2 out of this, and we can put that in front if we like. How do we solve this? X squared plus x plus 1. Well, we can't factor it because we need two things that multiply to get 1 and add to get 1. That doesn't exist with integers. If we find the discriminant, which is b squared minus 4ac, you could also complete the square. That would be cool as well. I wouldn't recommend it for this problem, but you could. b is 1, a is 1, and c is 1. End up with a discriminant of negative 3. Put this in the quadratic formula, and you substitute the numbers in. We're going to find that x is negative plus or minus I square root of 3 divided by 2, which means the roots for this are 2 that we were given originally, and these two imaginary ones. Suppose that a polynomial function h of x has the roots of negative 1 with a multiplicity of 1 and x equals 2i. What type of function is h? Give a reason for your answer. Now we're assuming that they're telling us as much information as they can without telling us everything. So we can infer some things. By the complex conjugate root theorem, if x equals 2i is a root, then x equals negative 2i is also a root. Since, tell you what, I'm going to change this to since x equals negative 1 is also a root, which we're told up here, multiplicity of 1, then there are 3 roots. So we got negative 1, 2i, and negative 2i. By the fundamental theorem of algebra, h of x is cubic. Find an equation with integer coefficients of h. Well, according to the factor theorem, since negative 1 is a factor, I'm sorry, I say that wrong all the time. Since negative 1 is a root or a 0, x plus 1 is a factor. Since 2i is a root, x minus 2i is a factor. Since negative 2i is a root, x plus 2i is a factor. So we're supposed to find the integral coefficients. That means they're integers. So this all needs multiplied out. Let's multiply the two conjugates together first. When you multiply two conjugates together, these two middle terms will always cancel out because it's always the same term with opposite signs. So we have x times x, which is x squared. Negative 2i times positive 2i is negative 4i squared. X times 2i is a positive 2ix. Negative 2i times x is a negative 2ix. So two middle terms will cancel out every time you multiply conjugates. And negative 1, an I squared is a negative 1. So this becomes x squared plus 4. And now to multiply this out, we multiply the x times each of these terms and the 1 times each of these terms. And we end up with h of x equals x cubed plus x squared plus 4x plus 4. Suppose that a polynomial function g has root of x equals 1, which has a multiplicity of 2, and another root of x equals 3 plus I. I wrote this answer in a little different order. X equals 1 is the root of multiplicity 2. By the complex conjugate root theorem, if x equals 3 plus I is a root, then x minus and x equals 3 minus I is also a root. Therefore, g of x has 4 roots, because we got this one twice and each of these once. 2 plus 1 plus 1 is 4. By the fundamental theorem of algebra, g of x is quartic. Find an equation with integral coefficients of g of x. Please try this on your own. Pause the video, and then you can unpause it when you're finished and see if we come to the same conclusions for this. That concludes these notes and this chapter. Hopefully you have spent a lot of time on this and work on some free response questions, and we can get this quiz and test done, and then we can start on the next chapter. Thank you very much.